Hello, my name is also Forsell and I am a senior automotive product manager here at the Qt company. Today, I'm going to talk to you a little bit about how to build immersive 3D environments and user experiences using Qt Quick 3D and why you should consider using real-time 3D in your next user interface project. After the session, I will be happy to continue the discussions and answer any questions you might have. So if any questions come up, or if you have any insights to share around this topic, please join me in the speaker lounge afterwards. The session will consist of some theory and some demos and live examples. I will begin the session covering the question of why should you use 3D in a user interface, which is something I surprisingly often hear from people coming from the mobile and desktop industries where flat 2D UIs are the norm. After that, I'll talk a little bit about the user interface trends we are seeing in the automotive industry and what requirements advancements in areas like autonomous driving and assisted driving put on the user interfaces. Essentially, why smarter machines require smarter and more adaptive user interfaces. And even though the examples I'll be going through are mostly automotive related, the same concepts and ideas are applicable to pretty much any embedded environment where you need to operate a machine through some kind of a digital user experience or user interface. And after that, we'll move on to some concrete examples that showcase what functionality and usability benefits you might gain from using real-time 3D. And the examples will be live demos built with Qt and shown through the Qt Design Studio tool. So let's get started and move on to the question, why do you need 3D in a user interface? When we look at the most common devices and applications we use in our day-to-day lives, it is quite clear that the majority of those user interfaces are quite flat and 2D based. This is true for pretty much anything ranging from your mobile phone, whether we're talking about Android or iPhone, as well as your PC or Mac user interface, your smartwatches, TV user interfaces, and so forth. And 3D is often reserved for things like gaming, where the addition of the third dimension brings not only aesthetic but functional benefits as well. It's much easier to do practical things like visualize your character's movement in relation to the environment when you do that visualization in 3D space. Other examples are, for example, showing the direction of the movement, expressing character emotions, providing more immersive experiences, and overall just building open worlds, which are pretty difficult to do in 2D format because you don't have the access to all of the different directions you would have in a 3D space. Of course, there are hundreds of examples of incredible 2D games that are immersive and complex, but generally speaking, the use of 3D allows you to visualize much more complex information in the same number of frames you would be able to do compared to 2D. In this example that I have in here, we have two stills from two very different games. We have one from a Tomb Raider game, and then we have one from the classic Super Mario Bros. From Nintendo 8-bit. However, even though the games are very different, the action taking place in both of these scenes is very similar, jumping over an obstacle. In the Super Mario example, the visualization is rather simple, and the only variables you as a player need to think about is the distance of the jump and the position of the enemies so that you don't accidentally hit them and die. However, when we move on to the 3D example, suddenly we as the player get a lot more information on what's happening just by quickly looking at the scene. First of all, we can see that the end destination which is the green ledge you can see in the bottom left corner, is quite a bit lower to our current position. We can also see that the ledge we want to reach is way too far for us to just directly jump there. We also can see that there is a rope slackline leading towards the ledge we want to reach, but that said rope is a bit to the right and a few meters down from our current position. And with this information, we can deduct that the only way we can get to the destination is through the slackline, and we can estimate how long of a jump and into which direction we need to make in order to reach the slackline, catch it between the chain we have, and then slide down and reach the ledge. And when I say all of this out loud, it sounds like a lot and it sounds really complex. But in reality, conveying huge amounts of information extremely fast in a single view would be quite difficult and unpractical in a 2D environment, but when rendered in a 3D space, like we see here in the example, deducing all of this information takes only a second of viewing the scene. Because 3D is the most natural way for us humans to intake and comprehend complex information. And this is because we live in a 3D world, and when information is visualized in this natural context, things like depth, distance, direction, and velocity, all mumbled together, can be understood by anyone, even if they have never attended a single physics class in their lives. And of course, there are more accurate ways to depict information like this in 2D, but let's be real, how many of us can actually remember the equations of motion, and how long would it take to understand the given information? And what would be the context where an UI would benefit from this type of flat 2D graph visualization instead of showing it in a 3D space? Well, now that I think of it, considering this is a developer summit, quite many of you probably do remember the equations of motion. And I'm also pretty sure that at least few of you immediately stopped listening to whatever I'm saying once the equation popped up, and now you're feverishly trying to figure out which equations of motion I'm showing here and what the graphs are depicting. But seriously, ain't nobody got time for that. When catering to the masses, it's better to leave the complex calculations to the computers and use simple and effective methods of visualization to relay the conclusions to the end user. And based on the examples before, it's quite clear that 3D brings in a lot of benefits when trying to visualize more complex ideas at once to the end user. And as technology progresses and the machinery we use gets smarter and smarter, the information we need to relay to the user is getting more and more complex. Hence, the possibility or need to visualize information in 3D space. And this trend is especially apparent in the automotive industry, where cars are equipped with huge amounts of sensors, and technologies like autonomous driving and collision prevention systems require even more going forward in order to be fully functional and safe. And the amount of computation that happens behind the scenes just to keep us safe on the road is quite astonishing actually. Let's take a look at this example. So here are some stats from an electric vehicle manufacturer, Lucid Motors, and their recent release, Dream Drive, for their Lucid Air vehicle. And according to their website, the vehicle comes equipped with 12 visible light cameras, 5 radar units, 4 surround view cameras, 12 ultrasonic sensors, and a lidar system or a light detection and sensing system on top of that. So just looking at the number of different sensors, the amount of data going through the computer on the back end every single second is quite immense. And when you look at the number of sensors modern cars have and add in the fact that there's a humongous number of changing factors ranging from weather to road conditions to other vehicles to pedestrians and whatever might be happening within the car, the amount of information available is vast, to say the least. And this will require some novel ways of visualizing this information in a way that is clear to the driver. And this in turn poses a huge challenge when designing and developing the vehicle user interface. First thing always to consider in a car user interface is safety. First of all, the information must be clear and easy to understand in order to avoid any misunderstandings that could lead into dangerous situations. A good example of this is clearly differentiating how the UI looks like when the car is autonomously driving versus when the driver is expected to steer the vehicle themselves. Any confusion between these different states could be potentially fatal if the driver does not understand what are their responsibilities at that specific moment. Second of all, the information needs to be relevant to the situation at hand. If the UI showcases a lot of irrelevant information, the driver might miss the critical info, which again might lead to unfortunate situations. Or on the other hand, the UI might be so full of detailed information that the driver gets distracted by it, and again, the end result will not be good. And then thirdly, the information needs to be accurate when compared to the real environment outside of the car. So if you are trying to visualize information to, for example, to prevent collision, you better make sure that the objects are where the UI tells you they are in comparison to the UI, or when comparing the UI and the real world to each other. And one good example of this are the parking assistance systems you can see, for example, in this slide. So modern cars have moved quite far from the more traditional reverse camera feeds in these kind of complex 360 visualizations as seen in the picture here. And these types of approaches can be quite helpful in tight spots like in cities and busy parking lots where you need to be wary of pedestrians, bikes, and other traffic coming in from various different directions. And when you're visualizing information like this, it is of utmost importance that the information is accurate. Otherwise, the driver will either not trust the system and will never use it, or they will trust the system that is showing inaccurate information and then end up crashing the car or hitting a pedestrian, which is not really a side effect that you want from your car UI. And this is where the benefits of real-time 3D come in full force. You're not just able to visualize the space accurately, but you're also able to change the rendering dynamically based on parameters coming from the sensors as it happens. So you're able to reflect the actual real-time, real-world situation within your UI. And this is important because it is practically impossible to predict every possible real-world scenario beforehand and prepare for those in your UI. And even if it was somehow magically possible, having to create graphical assets and setups to visualize each possible scenario would be a humongous amount of work. However, when you're dealing with real-time 3D, you can change the visualization in real time based on what the sensors pick up by altering the properties of your 3D representation. And this in turn makes certain that your UI is kind of future-proof, and it is also able to function in pretty much any situation that might happen. And of course, there are dozens more examples like this related to advanced driver assistance systems and autonomous driving use cases. For example, one of the use cases could be visualizing other cars and pedestrians in relation to you on the road, like you see in the top left graphic. Then you could also, for example, highlight vehicles in your blind spot in order to prevent switching lanes and accidentally crashing to a car you're unable to see because they are in your blind spot. Of course, visualizing cars' intentions in autonomous driving use cases is extremely important because one of the core challenges we have when moving from manual driving to autonomous driving is building the trust between the driver or passenger and the machine, so that the driver/passenger understands what the car's intentions are and why they are making those decisions. But yeah, this has been enough theory for now. Let's now look at a couple of simple examples of the functional benefits of real-time 3D from these examples that we have made with Qt Design Studio. The first example I want to show you is a simple road bending effect. In this project, we have a 3D mesh for the road and a very simple texture with the lines for the center line and the outside lines. And a custom material with a couple of shaders attached to it that create this bending effect. The shader properties are binded to the value of this 2D slider we see in the center, so we are able to dynamically bend the road as the value is being changed. In a real-life application, you might be getting the road curve information either from a navigation service or through the car's LiDAR and sensor systems, and then change the bend properties appropriately to create this dynamic bending effect that matches the real-life conditions outside of the car. So let's take a look at how this demo is actually done. Here we can see our project within the Qt Design Studio. Here we can see the form editor that has the 2D representation of the project. So we can see, for example, the 2D slider in here. We can see it here in the navigator. And then here we can see the slider properties. Here in the 3D editor, we have the 3D scene, which in this case is rather simple. It's just the road mesh with the camera and the lighting. So I can freely toggle around in this 3D space and view my application from that perspective as well. And then of course we have the live preview that we just viewed earlier that showcases the complete application or all built together. So here. So the project structure is really simple. We have a View 3D element in here, and within that we have a scene environment. Under that we have the light, we have the camera, and then we have the road element. And all of the effects that you are seeing here are actually happening within the road element. So let's go and click Edit Base Component to see what's going on within this element and how the bending effect has been achieved. So here within this element, we can see that it consists of a root node. It consists of the road element that we can see here in the 3D space. And that road element has a custom material attached to it. And when we look at the custom material, we can see that we have set the shading mode to shaded. So it means that it will take into account the shaders that we have added to it. And then we have added two different shaders to it. So let's take a look at the shaders in question. So we have the road vertex shader, and then we have the road fragment shader. I have opened both of the shaders in a text editor just for convenience sake, so we can see what the code is like. And when we look deeper into it, we can see that the shaders are rather simple. So this vertex shader essentially just refers to the UV map and then adds a bend effect to it. Then within the root node of the component, we have a custom property called bending. And the property value here is set to 0, and it's a property type is real. So this means that we will be using this custom property to control the bending value from the shader. So let's go back to the main application. So now we're back at the main view. So let's take a look at the road element. So here we can see the custom property that we just viewed called bending, and we can see that there is a binding created already. And that is the binding that we saw earlier that was automatically created to the slider. But I'm going to remove it for now so that we can take a look at how that is actually done in the Design Studio. So I'm going to start up the live preview so we can see the changes live as we do. So since I removed the property, you can now see that the slider doesn't work anymore. So let's recreate this effect. So we see this bending property here, and we can edit the property. So if we set it to +2, we can see that it turns a little bit to the right. And then if we set it to -2, we can see that it turns a little bit to the left. Then if I now want to bind this property value to the slider, all I need to do is click here, set binding, and then in the binding editor, select the bend slider that I want it to transform to or bind to. And then I just select the value property and press OK. And now, as you can see, I have the slider binding done and it works again. But I don't really like how this bending happens. So one thing I could do is control the minimum and maximum values of the slider. So I click the slider and I can go view its values. And I can see that currently the values go from -5 to +5. So I can move this to -10 and put the maximum to +10. And then now suddenly when I move the slider, I can see that the bend is a lot more stronger. Now, if I want to go even further, I could add, for example, some visual effects to my project. So one of these could be, for example, depth of field. So I have searched for depth. So I'm gonna take the depth of field component and drag and drop it to my scene. So now I've added this new effect component to my scene. Its properties state blur amount, focus distance, and focus range. But as you can see, nothing is happening. This is because I need to still add it to my scene environment. So I selected the scene environment, and its properties, I can select the effect that I want it to have. So depth of field HQ blur. And now you can suddenly see that the road, the further it goes away, the more it blurs out. But I don't really like how this looks. So let's go and move these amounts a bit. So let's lower the blur amount. Let's change the focus distance, for example, to 300. And maybe put the focus range to 200. And now we can see that the effect is a lot smoother and better looking. And that's it for the demo. A very simple way to achieve this dynamic road bending functionality that you can use in your ADAS projects or any dynamic UI that you want to create. So let's move on to the second demo. In this example, we have a 3D ADAS scene where we have two vehicles and we can change the distance of the vehicle in comparison to each other. We have the road component, and then we also have some moving terrain around us. just to make it a little bit more immersive environment. So the vehicle is not just standing in space, but it is actually driving in an environment. Very similar to the road bending I just showed you, we have a lane changing indicator implemented in this demo with a little bit more complex bending properties. This bending example is implemented using bone animations that allow for a little bit more precise and complex control over the bending compared to the shader example I showed to you earlier. And we have binded the animation and the transformation of the bending to the distance between the two different vehicles. So we can see that the indicator dynamically changes depending on how far away or close by the other vehicle is. So let's take a little bit deeper look into this demo project, because there's also some pretty cool examples of some of the other benefits of rendering your application in 3D space. And one of the cool things is that when your application happens or when your UI resides in 3D space, you can do some pretty cool camera transitions. So having these cinematic movements between different views and have the camera animate instead of having the UI objects move. And of course, we can change the materials to the ones we want. So now we can go to the night mode, and all of the same transitions and movements are possible between these stages as well. So when you are building these 3D environments, you can get a lot more immersive experience, and you can get quite creative when you are doing these transitions and animations. So that's enough examples for this session. What I have shown you has been mostly covering some of the functional benefits of 3D, but that's just basically scratching the surface. If you're really interested in this topic, I really recommend checking out some of these other Qt World Summit talks that dive a lot deeper into the nitty-gritty of how things are done with Qt's tools. I especially recommend these 3 talks. So Laszlo's talk on shaders and materials for 2D and 3D contents in Qt 6. Then Jarko's talk on hands-on examples with particle systems, mesh morphings, and instance rendering. And then Andy's talk about virtual reality using Qt Quick 3D. And all that's left for me to say is that real-time 3D is pretty damn rad, and Qt 6, Qt Quick 3D, and Qt Design Studio together provide an excellent basis for any ambitious UI project. I really hope that you found this session enlightening, or at least even mildly entertaining, and might use it as a catalyst to explore deeper into our 3D offering and the plethora of new cool features in Qt 6. I thank you a lot for your time and staying through the whole session. If you have any questions or comments, I'll be hanging out in the speakers lounge for the next 30 minutes, so feel free to pop in and continue the discussion. Thanks a lot.